Modern antibiotics are running out of time. Shortages are hitting hospitals, resistance is rising, and the shelves we depend on are left bare. Yet history points to a solution, a fungus harvested from dead birch that predates penicillin by millennia, carried as a survival tool by Ötzi the Iceman himself. If this ancient weapon was trusted for 5,000 years, why did we abandon it? And what does Big Pharma not want you to know about it now? Because the era of convenient medicine is ending. The answer is hidden in the data, and what comes next will determine if you survive the collapse or become another statistic. Every modern hospital is built on a promise: the right drug delivered at the right time, no matter what. That promise is a myth. The entire pharmaceutical system runs on just-in-time logistics. Inventory is kept razor thin, warehouses are empty, and every dose is a bet that nothing will go wrong. But things go wrong. In 2023, hospitals across the United States reported critical shortages of antibiotics like amoxicillin and piperacillin. Tazobactam. 8 out of 10 hospitals could not fill their orders. Children's wards rationed medicine, while doctors scrambled to find alternatives for sepsis and pneumonia. In Europe, the winter of 2022 left entire regions without access to basic antibiotics for weeks because a single factory in Asia paused production. It is not just antibiotics, IV fluids, insulin, even saline. Every drug that keeps the system running is a hostage to shipping lanes, customs delays, and the whims of distant suppliers. Supply chains stretch across oceans and continents, relying on a handful of manufacturers to feed millions of patients. When one link snaps, the whole system grinds to a halt. Pharmacies receive partial shipments or nothing at all. Emergency rooms improvise, sometimes with tragic results. This is not a glitch. This is the design. Efficiency is prized over resilience. Patents lock up the formulas, while production is centralized in the cheapest possible locations. The result is a single point of failure that can leave a city or a country exposed. The World Health Organization warns that antibiotic resistance is rising fast, but the real threat is simpler. The drugs themselves are vanishing from the shelves. Dependence on a fragile, patent-driven supply chain is not a strategy, it is a liability. When the trucks stop rolling, medicine stops flowing. In that silence, infection wins. The forest does not run out of stock. The birch tree does not wait for a shipment. The solution is not in the warehouse, it is growing on dead wood right now. Bacteria have learned the rules of our game. Every antibiotic we invent, they counter. In 2019, the World Health Organization estimated 1.27 million people died from drug-resistant infections, more than malaria or HIV. That number climbs every year. The CDC 2023 report shows resistance rates among common pathogens have doubled since 2015. MRSA, once a hospital rarity, now stalks schools, gyms, and homes. In the United States alone, multi-drug-resistant infections jumped 15% in a single year. The arsenal is shrinking. Of the 18 major antibiotics approved for use, only 2 new ones reached the market between 2017 and 2023. Bacteria are not waiting for the next shipment. They are already inside the walls. This is not a future threat. It is an active siege. Hospitals ration the last vials of vancomycin as superbugs sweep through intensive care units. Pediatric wards face a 20% spike in untreatable infections after routine drugs run dry. In Europe, the winter of 2022 saw entire regions without access to basic antibiotics, and the trend lines only point up. The World Health Organization warns of a post-antibiotic era where routine surgery carries the risk of death from a simple cut. The enemy is not just scarcity, it is adaptation. Resistant bacteria outpace our drug development, exploiting every supply chain failure, every patent bottleneck. The more we depend on synthetic solutions, the faster nature finds their weaknesses. The pharmaceutical pipeline is a single fragile line. When it breaks, the only defense left is what you can find, extract, and deploy yourself. The clock is not ticking, it has already run out. The forest does not care about patents or shortages. It produces solutions on its own schedule. When modern medicine fails, the only question is whether you know where to look. In September 1991, high in the Ötztal Alps near the border of Italy and Austria, a team of hikers stumbled across a body emerging from the melting ice. The altitude was 3,210 meters. Hostile terrain, a place where nothing survives by accident. Archaeologists soon converged on the site, extracting not just the remains of a man, but a complete kit of tools, weapons, and personal effects, frozen in time for over 5,000 years. Among the copper axe, arrows, and flint knife, 2 small fragments of fungus were found, each just a few centimeters across, pale brown, tough as old leather. These were not random debris. Both pieces were threaded onto a thin leather thong, knotted and looped, and carried at the hip. The context was intentional. Later laboratory analysis at the University of Innsbruck confirmed the species as Piptoporus betulinus, Birch Polypore. Spore structure, hyphal patterns, and chemical signatures matched only this fungus. There were no spores present, but the chitin and trimitic hyphae were unmistakable. DNA barcoding in 2012 at the Iraq Institute matched the sample to modern Birch Polypore with 99% certainty. Every artifact was catalogued, preserved, and transferred to the South Tyrol Museum of Archaeology in Bolzano, Italy, where Ötzi and his kit remain under climate-controlled glass. The museum conservation reports, field notes by lead archaeologist Konrad Spindler, and later CT scans all agree the fungal fragments were not food, not fuel, but an intentional part of the loadout. The evidence is physical, chemical, and contextual. No other explanation fits. The timeline is anchored. 5,000 years ago, on a glacier above the tree line, a man risked his life to carry this fungus. The question is not whether he had it, but why. 2 pieces of Birch Polypore, each about the size of a thumb, were threaded onto a leather thong, deliberately carried, not dropped or lost. The thong was looped and knotted, worn close to the body, positioned for quick access. This was not a ritual amulet or a lucky charm. The texture of the fungus tells the story. Dense, cork-like, impossible to chew, and bitter enough to trigger a gag reflex. No one carries this for flavor or calories. The surface is tough, layered like a shield, and when sliced thin, it flexes without breaking, a property that would matter to someone who needs a field dressing that won't fall apart in the cold. Every artifact in Ötzi's kit had a purpose. Copper axe for defense and woodcutting, flint knife for skinning and shaping, fire kit for survival. The fungus is no exception. Chemical analysis confirms the presence of betulinic acid and piptamine, compounds with known antibacterial and anti-parasitic effects. Ötzi's remains show whipworm infection and healed wounds. The fungus was not food and it was not fuel. It was a tool, a portable pharmacy engineered by necessity. Modern lab work matches this ancient logic. The same compounds found in those fragments are now recognized for their ability to disrupt bacterial enzymes, neutralize parasites, and create a sterile barrier on wounds. The evidence is physical, chemical, and practical. 5,000 years ago, a man facing death from infection or parasites carried Birch Polypore as his last line of defense. The logic is as clear now as it was then. When the system fails, the only medicine that matters is the one you can carry, deploy, and trust to work in the field. Strip away the bark, and the machinery inside Birch Polypore comes into focus. This is not a single-purpose organism. It is a chemical arsenal engineered by evolution to survive on dead wood and defend itself against the microbial onslaught that rots forests and flesh alike. 2 compounds form the backbone of its payload, betulinic acid and piptamine. These are not folk remedies or vague extracts. They are defined molecules, each with a distinct mode of action. Betulinic acid is a tritopene, a molecular structure built from 6 isoprene units shaped like a fortress wall. The fungus does not make it from scratch. It pulls it from the birch tree, refines it, and concentrates it within its own tissues. This compound is known for broad-spectrum effects. In laboratory conditions, it disrupts viral replication, it triggers programmed death in cancer cells, and it calms inflammation by blocking key enzymes. It is not water-soluble, which means it resists dilution and lingers where it is needed most, on the surface of wounds or in the gut where infection takes root. Piptoamine is a peptide, a short chain of amino acids, smaller and more agile than bulky triterpenes. It acts as an antibiotic, targeting bacterial cell walls and disrupting their integrity. In controlled studies, piptoamine has shown activity against strains like E. coli and Bacillus subtilis. It does not just slow growth, it punctures defenses and causes bacterial cells to collapse. This is molecular sabotage, not brute force. The synergy between betulinic acid and piptoamine is not accidental. One disables, the other destroys. Together, they form a dual action system, one for viruses and inflammation, one for bacteria and parasites. This is field medicine at the molecular level, a portable lab engineered by the forest, ready for deployment when every other supply chain fails. Inside Birch Polypore, the chemistry isn't random. It is engineered for survival. Each molecule has a job. The outer layer, dense and cork-like, acts as a physical barrier, but the real action happens at the microscopic level. Betulinic acid, scavenged from the birch host and concentrated by the fungus, is more than a passive shield. It disrupts the machinery of invading microbes. In laboratory models, betulinic acid blocks enzymes that bacteria use to break down tissue and form biofilms, cutting off their ability to spread. It also interferes with viral replication, jamming the gears that viruses rely on to multiply. This has been demonstrated against pathogens like E. coli and even HIV in controlled studies, though the leap from petri dish to hospital bed is still under investigation. Piptoamine is the second weapon. Piptoamine is a peptide antibiotic that targets bacterial cell walls, puncturing them and causing the cells to collapse. Unlike broad-spectrum drugs that wipe out everything, including beneficial microbes, piptoamine works with surgical precision. Laboratory results show effectiveness against gram-positive and gram-negative strains, including those that have begun to shrug off conventional antibiotics. There is no data yet on direct head-to-head comparisons with penicillin or vancomycin, but the mechanism is clear. This is sabotage at the molecular level. Beyond killing microbes, Birch Polypore's structure absorbs fluid and binds to wounds, creating a sterile field. The polysaccharides in its flesh stimulate the immune response, priming the body to fight infection. When sliced thin and pressed to a cut, the fungus acts as a styptic, arresting bleeding and sealing the wound, all while delivering its chemical payload directly to the site of injury. This is not folk magic, it is a multi-role system: antiseptic, anti-parasitic, styptic. Each function maps to a molecule, and every effect is grounded in laboratory evidence, not legend. Every tool is only as reliable as its identification protocol. Birch Polypore is not a generic mushroom. It is a specialized component built to specification by the forest. The first rule is non-negotiable. It only grows on birch. Silver birch, paper birch, downy birch. If the host is not betula, the target is invalid. Ignore anything on oak, pine, or willow. The second rule is structural. Look for the bracket form jutting from the trunk, shaped like a thick pancake or a horse's hoof, never a cap with gills. The upper surface is smooth, pale brown to gray, sometimes with a suede finish. The underside is diagnostic, pure white, densely pored, never gilled or spongy. Scratch it. There is no color change. The flesh inside is tough, cork-like, impossible to tear by hand. Misidentification is not just a wasted effort, it is a system failure. Some lookalikes, like tinder fungus or false polypore, share the bracket shape but betray themselves by growing on non-birch wood or displaying a yellowish or dark pore layer. The margin of error is slim. If the fungus is not on birch, or if the underside is anything but white and porous, abort the harvest. To remove, grip close to the base and twist sharply. The whole structure should break away cleanly from the trunk, exposing the pale flesh inside. Do not cut or slice at this stage. Leave processing for later. The goal is a single, intact unit, free from bark or rot. The right specimen is a factory-sealed component ready for deployment. Identification is not a game of chance. It is a protocol. Follow it, and the forest delivers exactly what the system cannot. Slice the outer skin of Birch Polypore into a strip about as wide as your thumb and twice as long. The texture is dense, flexible, and resistant to tearing. This is not a random scrap of fungus, but a ready-made field dressing. Press the strip directly onto a fresh wound. The porous white underside draws fluid, while the outer skin acts as a barrier, sealing the site from dirt and microbes. Within seconds, the surface clings to skin. No adhesive required. This is a structural solution. The polysaccharides bind to the wound, and betulinic acid lingers where bacteria try to invade. The entire patch holds its shape even under pressure. In field conditions, a strip of Birch Polypore can arrest bleeding and create a sterile field that outperforms gauze. If infection risk is high, prepare a decoction. Simmer 5 to 10 grams of dried ground fungus in 1 liter of water for an hour. The result is a bitter, cloudy liquid. This is not a comfort tea, but a solvent for extracting immune-activating glucans and triterpenes. For a more concentrated dose, use high-proof alcohol to create a tincture, dissolving the betulinic acid that water leaves behind. Follow the ratios: 1 part fungus to 5 parts alcohol, steeped for at least 2 weeks. Store the result in a dark bottle. It is shelf-stable, portable, and ready for deployment when the grid goes down. The forest does not care about expiration dates. With Birch Polypore, you build your own pharmacy, 1 cut and 1 simmer at a time. Today, antibiotic shortages and drug resistance outpace our supply chains. While pharmaceutical patents expire, Birch Polypore keeps working, unbranded and unbroken, growing wherever birch falls. No corporation controls this field medic. As nature's own refinery, it is a backup system modern medicine cannot erase. When the grid flickers, the real question is, will you recognize the tools waiting in the woods? Thanks for watching. Share your thoughts below.